Assalamualaikum and hi everyone. Alright, so this should be your last tutorial for this week. Okay, so we already discussed on how to write down differential rate law and then to write down rate law based on the problem statement given to you. Okay, and then I have been introducing to you on how to use integrated rate law formula to solve problems relating to it, which we're going to find out the new concentration, the time taken for a reactions to complete or react. Alright, so in this one we're going to learn about how to determine the order of reaction. Alright, so before we proceed with the exercise that I give to you through the Google Classroom, okay, so let's recap. Okay, so according to the notes that I give to you, or you can also refer to the lecture note, okay, so there are three ways on how you can determine order of reaction. Okay, so the first one should be by using initial rate method. Alright, so that one is you have to compare between different experimental data. So we're going to run out the experiment in several sets, okay, at least 3 sets if you have 2 different reactants. Okay, so at least 3 sets, and they have to compare to get what is the order of reaction with respect to each reactant that is present. So you're going to have a tables of data, okay, for every different set of experiment. Okay, so for linear graph method, it's a trial and error method, okay, where you need to plot at least 2 different graphs, either for first order reaction or zero order or second order, any or 2 of these types of order of reaction, and which one gives you a straight line, okay, that will be considered as the order of the reaction for that reactant. Okay, and thirdly is by using half-life method, okay, where this half-life method is talking about you are plotting a graph of concentration against time. Okay, if according to your notes that I give to you for your first hour and second hour tutorials, okay, so there are 3 different conditions for your half-life for 3 different order of reaction. Okay, so if let's say for zero order, the half-life, okay, the first half-life and the second half-life and the next half-life will be different from each other. Okay, it's either it's increasing or it's decreasing with concentration. Okay, whereas if it's a first order reaction, the half-life is constant, either it's the first half-life, second half-life or third half-life. Okay, so we're going to discover about the order of reaction by looking at this value of half-life by plotting a graph of concentration against time. Okay, so we're going to talk about this more next week, and for this one we're going to just focus on initial rate method, which is I think this is the simplest way to discover or determine the order of reaction. Okay, because it just needs you to calculate instead of sketching graph, and sketching graph is not everyone kind of like it, but you need to learn in case in the exam they ask you to plot a graph. Okay, so let's discuss on the questions 6. Okay, so in this question it states that decomposition of formic acid to form carbon dioxide and hydrogen gas is a first order reaction with a rate constant. Okay, so the given unit for your rate constant is per second, so that one confirm that this reaction is the first order. So the question asks you to calculate the time taken, okay, for the mass of formic acid to reduce by 30% of its original value. Okay, since they don't give you the original concentration in molar, so we're going to use the concept of percentage to solve this problem. Okay, so 30% to reduce, that means we consider the original concentration is 100%. Okay, so A naught equals to 100. Okay, so ignore the symbol percentage, and it should be reduced by 30%, so minus 30%, so your new concentration is 70%. Okay, so you can also use 1.0 to replace 100, as well as 0.7 for the new concentration, but I'm going to stick with 170. Okay, so this is the first order reaction, and for first order reaction, okay, so the formula, the integrated rate formula is ln A naught over 80 equals to KT. Okay, so you have to memorize this integrated rate law formula. So I'm going to substitute the value into the formula. So ln 100 over 70, okay, equals to 1.0 times 10 to the power of negative 2 as negative 1 times t. So your time is in second because the unit of your rate constant is per second. That means the time taken is in the unit of second. Okay, so you will get your answer to be 35.67 seconds. Okay, just to remind you, okay, this statement is very crucial, okay, because sometimes they might say that calculate the time taken for the mass of formic acid to reduce to 30%. Okay, in this one is by 30%. That means 30% of the reactants has decomposed to form the product. So the remaining is 70%. But sometimes when they say mass of formic acid to reduce to 30%, that means the new concentration is 30%. So you have to be alert with the word that being used in the problem statement. Okay, so we are done with exercise 6. Let's move on to exercise 7. Okay, so this is the formations of iodine molecule, okay, with the rate constant of 7.0 times 10 to the power of 9 per molar and per second. Okay, so the question does not give you or state either this reaction is a first order, zero order, or second order. I mean, how are you going to identify is it a first or second or third order or whatsoever? By looking at the unit of the rate constant. Okay, so if you refer to your lecture note, okay, so they give you 3 different unit of rate constant that is being commonly used, that which is your zero order, first order, and second order. Alright, so this is a second order reaction, okay, because if it's a zero order, okay, the unit of the rate constant is m per second. Okay, whereas if it's a first order reaction, okay, it is per second. If it's a second order reaction, it is per molar and per second. Okay, you can try to derive the unit of the rate constant by using the general rate law equation. Okay, so you can derive. Okay, if you don't want to memorize, you can always derive the unit. Okay, so since this is a second order reaction, so the integrated rate law formula that we are going to use is 1 over 80 equals to 1 over N naught plus KT. Okay, so let's solve question A first, which they ask you to calculate the new concentration after 2 minutes. Okay, 2 minutes, if its initial concentration is 0.086. So time is 2 minutes. And since in the rate constant unit is in per second, that means this time taken you need to convert into second by multiply by 60, so you will get 120 seconds. Okay, so the original concentration given is 0.086 molar. So these are the 2 informations that they give you throughout the question, including the rate constant. Okay, so now we can solve the question by substituting the value into our equation. Okay, 1 over 80, 1 over 0.086, okay, plus molar. It's 7.0 times 10 to the power of 9 per molar per second, and multiply by this times in second, 120 seconds. Okay, so you're going to solve it by rearranging the equation, and so you will get your AD is 1.19 times 10 to the power of negative 12 molar. So unit is very important. It's compulsory in every kind of questions that involve calculation. Okay, so let's move on to the question B. Okay, so in the question B, it asks you to calculate the half-life of iodine atoms if the initial concentration of iodine atom is 0.42. Okay, so they give you the original concentration, a new one. Okay, so the new original concentration is 0.42 molar, and they ask you to calculate half-life. Okay, so you can refer to the notes that I give to you for your first hour and second hour tutorials for the formula of your half-life. And just like the integrated rate law formula, you need to memorize as well. This half-life formula also you need to memorize. Okay, so for a second order reaction, our half-life formula is 1 over K A naught. Okay, so your K given here is 7.0 times 10 to the power of 9 per molar per second. And the original concentration given to you for this question is 0.42 molar. Always include unit in your calculation so you won't get confused. Alright, so if you press your calculator, you will get your half-life to be 3.40 times 10 to the power of negative 10 second. Okay, it's very small. That means in this reaction, okay, so the half-life is very small. That means it's quickly the original concentration quickly reduced by half. So this is the first half-life. Okay, alright, so we are done with the integrated rate law formula exercises. Okay, let's move on to a harder part. Okay, so this is what I've been talking about. Okay, so order of reaction, where you need to determine experimentally, not by stoichiometry relationship. So always remember this in your mind. Order of reaction cannot be used directly from the given stoichiometric coefficient. The stoichiometric coefficient is used to solve stoichiometry problems, okay, which is include balancing chemical equation, okay, calculating limiting reactants, determine limiting reactant percentage, and so on. Okay, but for this order of reaction, okay, it's you need to discover it experimentally. So for 3 different methods that is commonly used. Okay, unit of rate constant is is just in the question. Okay, so this one I don't consider it as a method. Okay, it's just based on the given problem, just like we done in our question 7. Okay, previously. Okay, so these 3 are the important methods: initial rate method, linear graph method, and half-life methods. Okay, so initial rate method is the one with calculation. Linear graph and half-life method is more on graph. Okay, sketching graph. Alright. So the difference between this linear graph and half-life method, in the linear graph method, we are going to refer to the integrated rate law formula to plot a graph. Okay, for example, if it's a first order reaction, we know that it's ln AT equals to ln A naught plus is minus KT. Okay, KT. So that means if you need to plot a linear graph, we're going to compare this equation with y equals to mx plus c. So this is my y, this is my c, negative k is my gradient, and t is my x-axis. Okay, so if I plot a graph of ln AT versus time, I should get a straight line like this with a gradient equals to negative k. Okay, so if it is a linear graph method, that means you need to refer to the integrated rate law formula to know what should be the y-axis and what should be the x-axis. Okay, and you will expect what kind of graph. Okay, if the compound that we draw based on the data we obtain, okay, so based on the concentration, we're going to obtain a result of concentration and time. Okay, what is the concentration after several different times. Okay, so if we plot that graph and we get a straight line exactly like this, that means the reaction is the first order with respect to that reactant. But even though if we plot ln AT versus time, okay, with the same data, but we don't get a straight line, but instead we get a different kind of graph lah. Whatever it is a curve. Okay, so if it's a curve, that means the integrated rate law formula does not fit with the order of reaction for that reactant. That means the reactant is not a first order reaction. It must be a different order reaction, either 0 or a second order. So that's why I refer linear graph method as a trial and error method, because you need to plot more than one graph, and I don't kind of like it because it consumes me so much time. But still, you need to learn and understand about it in case in the exam they might ask you. Use linear graph method to determine the order of reaction. Okay, whereas in the half-life method, you just need to plot a graph of concentration versus time, and from there, okay, you need to identify a different value of half-life. Okay, so if let's say we start with 100% concentration, okay, so and then when it's dropped by half, 50%, so at this time, this is the first half-life. Okay, and then it drops to 25%. Okay, from the original concentration. So 50 to 25 is half of it. So that means this is another T half. This is your second T half. Okay, and then you're going to discover the third one. So from here, half of it becomes 12.5%. So this is the third T half. Okay, so so you're going to compare between these three different value of half-life. Okay, if it's a first order reaction, the half-life will be the same for the first, second, and the third. Okay, but if it's a different order of reaction, either 0 or second order reaction, okay, so one of it, you will have a greater value of half-life at greater concentration, and another one of it will have a smaller half-life with a greater concentration. Okay, so this one again I'm going to discuss with you next week, okay, in another tutorial. So for today, we're going to focus only on initial rate method. Okay, alright guys, so let me teach you how to use initial rate method to determine the order of reaction in this exercise 8. Okay, so in my previous example that I give to you through the notes, okay, I used the concepts of concentration, but in this time is in the terms of pressure. Okay, so it's just still the same, but it's in the pressure. So you just need to consider about the unit. Remember about the unit. Concentration and pressure has a different unit. So let's write down first the general law, rate law. So K, okay, so it's a pressure, so it's a round bracket instead of square bracket. So H2 to the power of X and ICL to the power of Y. Alright, okay. So if I want to determine the order of reaction for my hydrogen, okay, that means I need to make sure the pressure of my ICL is being kept constant. Okay, so if you refer to the given data, okay, so set of experiment 1 and set of experiment 3 have a constant pressure for my ICL. Okay, so we're going to compare experiment 1 over experiment 3. Why do I put experiment 1 on the top? Is because the partial pressure of my hydrogen is greater in experiment 1 and the rate of reaction is also greater in experiment 1 compared to experiment 3. I don't want it to leave it out in the form of fractions, so that's why I put a greater number on the top and then divide with a smaller number. Okay, so let's substitute the general rate law with the value. Okay, so K, partial pressure of my hydrogen is 250 to the power of X and 325 to the power of Y for my ICL, which is equals to 1.34. This is my rate of reaction over K, 50 to the power of X, 325 to the power of Y. So it's over 0.266. Okay, and then cancel out anything that is possible and try to simplify the values. Alright, okay. Okay, so this one becomes 5 and this one becomes 5 as well. So it becomes 5 to the power of X equals to 5 and 5 equals to 5 to the power of 1. So my X is equals to 1. Therefore, write a statement: first order reaction with respect to H2. Okay, because X is for H2. Okay, let's discover for my ICL. Okay, so in ICL, okay, so we're going to compare experiment 2 and experiment 1, because in these two sets of experiment, I have a constant partial pressure for my hydrogen, and my partial pressure of ICL is greater in set of experiment 1, therefore experiment 1 will be on the top. Okay, so K 250X, okay, 3 to 5 Y equals to 1.34 over K 250X 81 to the power of Y over 0.331. Okay, simplify, cancel out anything that is possible. So this one, if we solve it, we'll get it to the number of 4, and this one is number of 4 as well. So 4 to the power of Y equals to 4 to the power of 1. Okay, because 4 is actually equals to 4 to the power of 1. So Y equals to 1. Okay, therefore first order reaction with respect to ICL. Okay, so overall order, write down first the rate law. So overall order, you just need to add up both individual order of reaction, which is 1 plus 1 equals to 2. So second order. Okay, just to remind you, why do I use a round bracket here is because we use concept of pressure in this question. If it's a concentration, it must be a square bracket. Okay, let's move on to the next question. Alright, so you're given this NO and Cl. Okay, just now we use in the terms of pressure, and this time is in the terms of concentration. Okay, so let's do the same. For determining the overall order of reaction, we're going to start with 4 NO. But before we start, let's write down the general rate law. Okay, NO to the power of X and Cl2 to the power of Y. Okay, so if I want to identify the order of reaction for my NO, that means I need to make sure the concentration of my chlorine is being kept constant. And in this case, these two, experiment 2 and experiment 1, have the constant concentration of my chlorine. Alright, and the rate of reaction and the concentration of NO is higher in experiment 1. Therefore, experiment 1 divided with experiment 2. Okay, so it becomes K 0.030X 0.010Y over K 0.015X 0.010Y equals to 3.4 times 10 to the power of negative 4 over 8.5 times 10 to the power of negative 5. Okay, let's solve it. Okay, so if we solve it, okay, this one, simplify, it becomes equals to 2. Okay, cancel out, cancel out. Okay, and this one, it's become 4. So 2 to the power of X equals to 4. So 2 to the power of X equals to 2 to the power of 2. Therefore, X equals to 2. So write the statement, second order reaction with respect to NO. Okay, so that is for NO. Now let's do for chlorine. Okay, so for Cl2, so I'm going to compare between experiment 3 and experiment 2. So experiment 3 on the top of experiment 2, because in experiment 3 I have a greater concentration of my chlorine as well as the value of my rate of reaction. Okay, so K 0.015X 0.040Y over K 0.015X 0.010Y equals to 3.4 times 10 to the power of negative 4 over 8.5 times 10 to the power of negative 5. Okay, try to simplify the equation. Okay, so cancel out anything that is possible. Okay, so if I cancel this one out, it becomes 4, and this one becomes 4 too, and this one cancel out. Okay, so 4y equals to 4, which is 4 means 4y to the 4 to the power of 1. So y equals to 1. Okay, write the statement. First order reaction with respect to Cl2. Okay, so determine the overall order of reaction. So rate equals to KNO to the power of 2 and Cl2 to the power of 1. So overall order, okay, 2 plus 1 equals to 3. So third order reaction for overall order of the reaction. Okay, next, calculate the value of the rate constant. Okay, so let's rewrite our rate law. Rate equals to KNO to the power of 2 and Cl2 to the power of 1. Okay, to determine calculate the value of the rate constant, we can use any sets of the experiment. So let's say I'm going to use my set of experiment 1. So I'm going to substitute the value of the experiment 1 into my rate law. So rate of reaction for experiment 1 is 3.4 times 10 to the power of negative 4 molar per second equals to my K to be discovered. Okay, concentration of my NO to be 0.030 molar to the power of 2 and Cl2 is 0.010 to the power molar to the power of 1. Okay, so let's simplify. Okay, so this one, it becomes 0.030 to the power of 2 times with 0.010 to the power of 1, whereas for my molar unit has become m to the power of 2 plus 1, so become m to the power of 3. Okay, so 3.4 times 10 to the power of negative 4 ms negative 1. Okay, and that one becomes 9 times 10 to the power of negative 6 m to the power of 3. Okay, so I'm going to bring everything from the right side to the left side so that it's going to left my K on the right side only. Okay, so simplify. So this one become 2 because we cancel out with the one at the top. So my unit of the rate constant m negative 2 as negative 1, and the value of my rate constant is 37.7. Okay, so please make sure when you calculate your rate constant, you need to always write down the unit. Okay. Alright, so guys, that's all for today's tutorial. I hope this video really helped you to understand to determine the order of reaction by using initial rate method. Okay, see you guys in my next class. Bye bye.